Good morning, Anvit.
Good morning, sir.
How are you?
Good, good, good. How are you?
Fine. After a long time.
Hello.
After a long time. After a long time. No? Hello. Hello. Hello.
Hello.
Hello, Anvit. Hello. Yes, Anvit.
Hello.
Hello, Anvit.
Sir,
Hello.
can you hear me?
Yes, yes.
Okay, okay. Cool.
So you got the share option on your screen, Anvit? Hello, Anvit. Hello. Hello, Anvit. Hello. Hello, Anvit. Hello, Anvit. Hello. Hello. Hello, Anvit. Hello, Anvit. Hello, Anvit.
ಕನೆಕ್ಟ್ ವಿನರೇ
Hello, Anvit. Hello, Anvit.
ಜಾಯಿನ್ ಮಾಡೋಣ ಜಾಯಿನ್ ದಿಸ್ತಾಗಿ
Hello, Anvit. Hello, Anvit.
Hello, sir.
Anvit. Hello, Anvit.
अन्वितचा म्यूट आहे बघा सर, म्यूट आहे.
म्यूट आहे पण मित्र आहे. हॅलो, अन्वित.
अनम्यूट करा की.
हॅलो, अन्वित.
अन्वितला अनम्यूट करायला लागेल तुमचं अनम्यूट आहे ते. हा केले ना.
Anvit,
त्याला ऐकूच येत नाहीये. Cannot get into it. तो रिजन होते.
Hello, sir.
yes, Anvit.
I can hear you now.
Yes. Some technical problems there.
Oh, okay. Yeah, are we waiting for more students?
Now we can start. Actually, YouTube live is going on, so many of be going through the YouTube channel.
Okay.
So we
So
can start.
should I join any other link or this is fine?
No, this is fine. Okay, no issue.
Okay, cool.
Okay,
I'll
so,
start.
so good morning, all of you.
Oh, you're on mute. Yeah.
So good morning, all of you. Welcome to the fourth day of webinar series on process engineering. So for today's session, we have with us Mr. Anvit Vartak, pass out batch 2013. He is an alumni of our college. Brief about the Anvit is he is a batch 2014 pass out. Then he completed his MS from University of Oklahoma, USA in 2016. There he worked as a graduate research assistant at Philips Heterogeneous Catalysis Lab to build kinetic models and develop zeolite catalysts for fluidized catalytic cracking units. Currently, he is associated with Sila Nanotechnologies as a process engineer in USA. He has successfully designed and scaled up processes to synthesize nanomaterials from biomass as a substitute for crude oil derived products. Currently working on scaling up of manufacturing of battery materials that improve the battery capacity by 20% compared to the Tesla. I welcome Mr. Anvit Vartak for this webinar on the topic sustainable efficient product development. Welcome Anvit. Now I request Anvit to start with the session.
Thank you, sir. Thanks for the introduction. So as sir mentioned, I'm going to start. Oh, let me just share my screen. Okay, can you see my screen now?
Yes, yes.
Okay. Okay, so I'm going to talk about creating a sustainable product through effective process development. What does that mean? Um, if we break it down, it's about innovating and designing processes to build sustainable materials to either replace materials that are currently in use derived from crude oil, or just come up with more innovative materials that can be very useful in sustainability and driving environment related positiveness throughout the world. So let's start with that. So the presentation outline is pretty short. I've divided into pretty big sections. Um, the first one is I'm just going to go through an overview of what's the platform for biomass to conversion into different types of chemicals, either specialty chemicals or commodity chemicals, or other materials that we currently use, which are very widely valued in the market and that form a very important part of our day-to-day life. The second part will be this idea of structure property relationships, um, which I'll dig deep into, which will be a very helpful tool that I've been using in designing processes and also developing different process flows to get to the material that you want to, starting with a different type of biomass derivative. And then how do we use that to tune material structure physically or chemically to build a good process. So how to develop the process, how to get to different unit operations and processes to get to your product. Um, so starting with a very high level overview of um, what is biomass as a feedstock. Biomass is anything that comprises of renewable resources that you see around us, that's made out of a hydrocarbon. So any food related items, any wood or trees related items are classified as biomass, or anything that's made from those items is also classified as biomass, as I've marked here as old corrugated cardboard, which is a lot of this cardboard that's used for packing and everything, and then we just throw it away as waste once we are done with it. Not most of it is recycled. So finding a way to use that to make different types of platform chemicals. My first job straight out of masters was with a company called Origin Materials, wherein I worked as a process engineer with their research team to develop the process to go through starting from that biomass to a very useful product that is already existing in the market. So there's this way of identifying what are you going to make with this biomass. You're given wood chips and you have to think, what do the wood chips comprise of? What are the building blocks? So from there we know that um, there's a lot of papers, there's a lot of literature study that says we can come up with intermediate chemicals which are building blocks for further chemicals. Like CMF is chloromethyl furfural, so it's a furfural derivative. HTC is hydrothermal carbon, so it's mostly comprised of solid carbon biomass. And then the applications are a lot of these end products, and to mark some of them are PET bottles that we currently use to drink water out of, any other beverages out of. um, Carbon black, which is used as a filler in tires to give it mechanical reinforcement and make natural rubber stronger. So the black color that you see for your tires is because there's so much carbon black in it, that makes it strong. So it's a very important component of that. And cars, meaning um, battery materials that helps us move towards electric cars and eliminate crude oil type gasoline and diesel and sources like that that are not good fuels for the environment. um, or in agriculture, where there's a lot of plastic or artificial chemicals being used currently that are detrimental to the plants. So if you start from a building block that's coming from the plants, it is not as harmful as the artificial chemicals are that come from crude oil manufactured um, type things. And building materials, you've seen a lot of people researching on making concrete out of waste that's generated from biomass and things like those. So to see what lignocellulosic biomass comprises of, and lignocellulosic biomass is the wood chips that I was talking about, the waste wood chips or waste old corrugated cardboard. It's a very heterogeneous mixture of cellulose and hemicellulose. These are all the C5s and C6 molecules that you have, and also lignin, which is a fairly complex polymer that you have in biomass. So understanding what it is made up of helps us knowing how you'll break it down and what chemicals can be made out of it. So this is the chloromethyl furfural that I was talking about. Can you see my cursor? So I'll be using the cursor quite a bit.
Yes, yes.
You can get to furfural, which is also a very good building block for a lot of specialty chemicals these days in the market, which can make a lot of polymers like PFA and other polymers, which are used as a lot of building blocks for the plastics that we use these days. CMF can go to levulinic acid, which also has a lot of applications in making different specialty chemicals that are widely used in pharmaceutical industries and all sorts of different other applications. But what happens when you're trying to make these platform chemicals out of this biomass? Um, Almost 50%, very close to 50% yield is all these things that I've marked. The CMF decomposes, meaning it is not a single molecule anymore. It starts getting polymerized and starts forming chains, and all these comprise of a very complex mixture of a polymer that you cannot break down or that you cannot resolve by chemical processes. So you end up with a in your reactor at the bottom, you end up with a sludge-like looking material which is absolutely useless to begin with. The top part is all these floating chemicals the three chemicals that I pointed out. So my job when I started at Origin Materials was to understand how to either break down this very heterogeneous mixture of sludge that's forming, or at least use it in some form or the other to create energy or something else. So you start analyzing what the material is made up of and start identifying what can you do to it to form different products, so build different products. And going back to this, since it's a hydrocarbon and you have only carbon, hydrogen and oxygen and a very small quantity of ash, what you can do is you can treat it at high temperatures, like very high temperatures, around 1000 C, 1200 C, to make all these volatiles go off and make it more and more carbon rich to the point where it gets to either activated carbon, carbon black, or other specialty products for agriculture, which have big markets. So there's a lot of demand for all these products. So let's see, how does structure property relationships as a tool help us? So this is the idea of understanding the structure of a material, and what properties it imparts to the material, and what do we see, what do we visually see, and then what happens if it's added to a certain thing, like carbon black added to tire makes it stronger, carbon black added to any other polymer makes it stronger again. So those type of things. So thinking of how structure property relationships are involved in our day-to-day life, you can think of, why is glass transparent when glass is almost made up of sand? Sand is not transparent. Why is glass transparent? So it's because it becomes crystalline when you melt all that together to form glass. And that crystallinity imparted to it makes it transparent. Why does drinking methanol um, dangerous compared to why ethanol isn't. We drink alcohol all the time, but it's not the same alcohol. It comprises of different inherent properties because of how its structure is, how its chemical structure is, how it reacts with our body. um, why do compounds have fixed boiling points? So all these questions are answered by this very strong, powerful concept, which is structure property relationships. And you can later read about it more. We use it in chemistry a lot. We use it in biology. We use it in engineering, unknowingly a lot of times. We just have to find out how we use it. So one very good example of how can that be applied into your day-to-day thinking is, think of diethyl ether and N-butanol. If you think of the molecular formula for it, you have the same number of carbon atoms, you have the same number of hydrogen and oxygen atoms in it, but only by knowing how it is bonded, how the different atoms are bonded to each other, you'll know that if it's going to be a stronger bond or if it's going to be a weaker bond, which determines its physical property, which is the boiling point. So I'm going to quickly skip through a lot of slides because we have a lot of things to cover. So if you have any doubts, you can write them down and ask me later at the end of the presentation. So what is structure? Structure comprises of these four things, which is the particle shape and surface morphology. How does a particle look at a microscopic level? Is it a sphere? Is it a rectangular particle? Is it like a shard of glass that's broken down? Things like those. What are the functional groups in the molecule? What is the elemental composition of the molecule? As we talked about in the previous example, the elemental composition is C, H, and O. What were the functional groups? We had alcoholic groups in one, we had ethers in the other. What is the basic framework of the material? How is it comprised of? How is it holding? So structure can also be extended to this larger scale, not just the atom that we are talking about. And there are different methods to know what the structure is, like NMR, FTIR, SEM, and all these different techniques. And we can discuss that later if you have more doubts. What are the properties that are imparted to certain molecules or certain compounds because of how its structure is made? They can be largely categorized into three different realms. One is chemical, the other is physical, and biological. So examples of chemical are how do compounds react with each other, or how do molecules react with each other. So you get reaction rates, you get heats of formation, position of equilibrium, and things like those. Physical are like the one example that we discussed, and also the crystallinity of glass, making it transparent, things like those. And biological, meaning the odor, the taste, toxicity, drug actions. So coming back to this idea of, hey, I have a sludge made from biomass. Um, what do I make it into? You start identifying different products that you can make and start thinking of an easier route to make something. So activated carbon is more complex to make. Agriculture products are difficult to get into the market because of the regulations around them, but carbon black is identified as a rather simpler product to get to, and less of those regulations around it. So let's see some examples of structures. We talked about structure being, in this case for us, being a particle, right? So one particle here in this example is a spherical particle, which is a nano-sized particle. How do you get to know how that particle looks? It's by SEM, so scanning electron microscopy. It is just a glorified optical microscope that can zoom in much more depth than you can normally do with your magnifying glass. So you can see that the scale here is 2 micron, and the particles are much smaller than 2 microns, and you can see the particles are nanomaterials because they are nano-sized single particles. And when these particles, individual particles, get chemically bonded to each other, they start forming an aggregate, and it can look like this. And an aggregate is then defined by its OAN structure. OAN is oil adsorption number, the technique that defines how long the chain of these particles is that we are talking about. And surface chemistry, like what are the different functional groups that exist in your particle. So all these types of different functional groups, and you can find out about those things by these spectroscopic techniques. The high level overview of these would be, if you see this magenta colored line, you see so many peaks, which means there are a lot of different functional groups that are being detected in your particle or in your material. And as you keep going down and down, you increase the temperature of heat treatment that I was talking about. So the process is called as pyrolysis. So this is parent material, which is untreated. This is as you keep on going, increasing temperature, 250 C, 500 C temperature treatments, and higher. When you get to the red line, it's 1500 C or 1200 C, in that range of heat treatment. And the black line that you see at the bottom here is the carbon black. So you can see basically carbon black doesn't have too many functional groups. It is very segregated. So we are trying to replicate that footprint, which takes our product close to carbon black in terms of functionalization. So there's a lot of carbon. That's it. We lose all the hydrogen and oxygen that's present in our material. Um, and this is TEM, which is tunneling electron microscopy. This doesn't show you surface characteristics, but this is helpful in knowing how many of these aggregates are formed in your material and how much do you need to break it down to get it down to a smaller particle size, so your material can be better in terms of reinforcing the rubber that you're using it as a filler into for the tires. So it is so well known that there's been hundreds of years of research gone into the carbon black industry, and they've also started nomenclature in a way that some parts of it tell you how the material behaves in the rubber. One digit tells you what's the primary particle size, the single particle that we talked about. And the other, the end part, the 60 circle that you're seeing, is telling you how long that chain of those primary particles is that we just talked about and that was shown in the picture earlier. And depending on those particle sizes, you know that smaller particles in rubber will impart more mechanical properties to the rubber and make your tires stronger. And as you keep on increasing the larger and larger particles used as carbon black in your rubber, your tires are not as strong as they would be with a smaller particle. So that's how it interacts. And that's why the surface area of that particle is important for us in interacting with the rubber. So more particles you have, more smaller particles you have more surface area of the particle, which acts as a filler in the rubber and interacting with the rubber that it surrounds with. So there's this different there are these different testing materials or testing methods that show you the properties that are imparted by different structures. So now we are in the properties section. So the properties of reinforced rubber, properties of your tire after you add the carbon black to the tire, and what happens when you either increase or decrease the particle size, and what happens to that. This piece that I've shown is the sample size that you take, that's cut out of the reinforced rubber, which has your carbon black added, and it's stretched using a machine which measures how long did it stretch before breaking, how much force was used to break that, which is the tensile strength, and then calculations of modulus and other things are also tested. So you don't have to really get into this, but this is a chart that shows how do properties of that reinforced rubber depend on what the structure of your material was. So an example is the surface area that I talked about. Surface area of your total material increases with how many small particles you have. And that's why increasing surface area means making smaller and smaller particles. It increases the hardness, abrasion resistance, and tensile strength of your rubber, which is eventually going to be used in making tires, which is better for us. Because if it's stronger, it lasts longer. If it has better abrasion resistance, it also definitely lasts longer. The other example is the OAN structure. OAN structure meaning, going back to this, how long is this chain that we are making of those one-to-one small particles? What happens when that OAN structure increases? Your aggregate size increases. Aggregate size meaning how long is it and how tightly are the particles packed. Elongation of this sample that we are talking increases if you have decreases if you have those longer chains, because then your particles can be broken down easily. Hardness increases of your sample, abrasion resistance increases, but you see no change in tensile strength. So now you know, when you're making samples, if your tensile strength is seeing no significant change and you want to increase it, you can try to tune your chemical reaction in such a way that you increase the surface area. But it's going to show you no change if you change that structure, that number of links of the particles that we have. So now we've identified what are the fundamental structures of your particle that we are talking about, the single carbon black particle that lays the framework to give you better reinforcement in the rubber that you have. So we know surface activity, like all these, which is related to the functional groups that are present in your material. Surface area and porosity. Surface area being how much of total area do you have in your overall material with exposed particles. So smaller the particles, more the total surface area. And porosity is, you can think of porosity being these small channels that you start creating inside your material when you start heat treatment of the material at higher and higher temperatures. The particle starts creating voids as you have those functional groups leaving that contain hydrogen and oxygen, while you're creating a more carbon rich product, which gives you more value. What is the aggregate fineness? Meaning all these single particles combined together, are they making a large clump or are they making a smaller clump? And what is the OAN structure? The structure that we discussed about, linkage of those single particles. Are they making a nice long chain or are they branching out? That also is very important for us. So now I'm going to talk about what the general development cycle looks. HTC is the hydrothermal carbon that I mentioned as a tire filler. So we've identified a product, we've identified a market for it. We know what our material was formed of and what properties it imparts. Now we've done all these things, but we have to get to the product and we have to define different unit operations or processes that we'll do to take us to that carbon rich product that we want to get to. So the usual cycle looks like, you identify your market, which is a tire filler, carbon black. You design its structure, or at least understand what does carbon black structure look like. So what I've shown here is all these planes of the heterogeneous aromatics that I was talking about, forming a planar substance. And depending on how those planes are arranged, you know how the structure is well tuned or if it's not. The process development cycle, wherein you keep going back and forth, understanding the structure and knowing what unit operations or what processes will make you get closer and closer to this structure that you want. So suppose I start heat treatment of the product with 500 degrees Celsius heat treatment, but I don't get to the structure that I wanted. I'll go back, either increase or decrease the temperature depending on what I saw, and see if I get to that. And once you are done with this, you move into a constant characterization and analysis phase, where I was talking about the optical microscopes or other techniques that show you what functional groups are present in your material. And then the processing of your product into where its intended market is. So this will be adding your carbon black to actual rubber and seeing the testing that I showed, seeing how it behaves depending on what material you add and how do you develop it. And that's when you start getting a matrix of, hey, a material that was temperature treated at 1000 C behaved well, at 500 C didn't behave well. A material with long chains of those primary particles behaved well, but with short chains and branching did not behave well. So things like those. So you start making a matrix of what works and what doesn't. The second part is, now we know what product we have to get to, but how do we really get there in real world? So these are some pictures of what we start with. The sludge that I was talking about, when you eliminate water, it's still a very clumpy type material. If you can think of wet mud that has absorbed a lot of water, how it is clumpy together and how you can just break it down. So you know that your end product is carbon black, which definitely doesn't have moisture. So the first step is getting rid of moisture. So you get there and then you start making different unit operations, linking them together and get to this final product, which has chemical and physical properties like carbon black does. And then you have a product that you've made out of biomass, which is a like for like replacement of carbon black, which was made from crude oil, which is not good for us. And you know that crude oil is a non-renewable resource, and we are going to keep needing these materials because we are so dependent on them. So we are trying to find alternatives to make from biomass. So as I showed you this first picture, we know that we have to get to a dry product. So the first step is knowing how much water is in there or how much other solvents are there in your compound. So after understanding that, you dry that material. You first let it through a high pressure filtration system so you can extract as much water as you want, um, and then store it in buckets. And when you have to process it, you pour it in trays, and those trays are put into a forced air convection oven. So you can imagine this of being like a baking oven that you see in large bakeries with a forced draft convection, meaning a fan that's there on the inside that drives the air currents and helps you dry faster and faster. So you do that, a very simple unit operation, you get to less than 2% moisture contents for your solids. But as we know, we need really tiny particles. We need very small particles. And these are not small particles. You can just visually see them and you know that they are bigger. So you start thinking of what different processes we go through and how do we get there. So always when you get a material, when you're done with a unit operation, check back with what you want and where you are. So right now, if we do the characterization techniques that tell us about the chemical structure and what functional groups are present, you still know that there's a lot of chemical functional groups present in there, but you want more and more carbon and something that looks very close to benzene rings attached together. The surface area and porosity. It's a technique called as nitrogen physisorption, wherein the nitrogen goes into your small particle, and depending on how much nitrogen went in, you quantify that, and you know if your particle is a solid particle or if it made those channels that I'd shown in one of the pictures there. The aggregate fineness, wherein those single primary particles that were sticking together, if they are making very small tiny aggregates, or if they're making these large agglomerates that we can see in this picture here. So we are still at those large agglomerates. And the OAN structure, as I talked about, which cannot be done on this material for some reasons that we can discuss later if you are interested. So we do a particle size distribution of these. It is very simple. I think you must have done that in the SFMO lab with solid fluid mechanical operations. You have sieves with different micron sizes, and you just use the sieve shaker to see what particle size you have, depending on how many particles pass through a certain size range. And that's how you define the percent mass that's there in these ranges. So now you see that there's not too many particles that are smaller than 45 micron ranges, and you have to get down to the really tiny micron size range, the single digit micron size range, and you still have these large 45 micron or 1400 micron, which is almost a millimeter, all those big chunky particles. So what do? We think of how we can break them down. So a very easy process that you can think of, or a unit operation that you can think of, is milling or grinding. So we pass the material through a grinder, and that's how you go from this material that we see these large chunks of to a nice fine powdered material. And when we see the particle size distribution on it, the coarse and Turkish is the type of mill that we use for to break down the particles. So Turkish setting is more effective. And non-milled, we can see that these black bars are so many more in the large micron size ranges. But as you go to this type of grinder or grind size, you start increasing your fine particles. Now we are getting closer and closer to what we want to get to in terms of carbon black. So smaller particles or smaller powder-like particles, when filled in tire rubber, interact better, provide more reinforcement. And this D90 is the 90 symbolizes 90% of mass passed through that sieve size um, before milling and after milling. So you can see a significant decrease in how much mass passed through the 250 micron sieve after milling. And D50 is 50%, 50 weight percent of that material passing through a certain sieve size. So you can see that earlier more than 50% of material was in this size range. Now we have a lot of material below the 45 microns. So we are now getting a very narrow and nice particle size distribution. But the idea here is to think of different ways in which you can work this out in a lab. So you don't have to spend thousands of dollars or lakhs of rupees in building a large size equipment or getting to a large size equipment and then saying, oh, this did not work. So what do? Look around for inspiration in day-to-day things that we use. So we use coffee grinders to grind down coffee beans to a small particle size powder, and then that is very useful. So we know that. So we use a coffee grinder, which is modified a little bit, feed the material from the top, and from publications, from literature or other articles, that using different settings on your coffee grinder, like this French press or drip setting or espresso setting or Turkish setting, gives you smaller and smaller particles. So that's what this Turkish was, the setting on the coffee grinder that was used to get from here to here, which is giving us a very effective change with a very cheap unit operation and a cheap equipment that we can use to just prove that we are getting to this material. And then when you scale up later, you go to actual equipment where you invest a lot of money. But that only happens after you prove that all these unit operations are working for you. Inert pyrolysis. So now we know that we have these fine particles. We have a powder that is very fine. But you want to get to carbon black, and just by looking visually at carbon black, it is a very dark black substance, and this powder that we have is definitely not that. So what do? Go back to our characterization, understand what it is made up of, and we know there's a lot of carbon, hydrogen, and oxygen, and we need to keep carbon in our material, in our final material, and drive off hydrogen and oxygen. So high temperature heat treatment methods are very commonly known to drive off all these functional groups that are volatile from your material and leave you with a high carbon content material. So we decide to go with a high temperature furnace, but now it has to be inerted, because if you have air in the system, the oxygen in your material is going to interact with air. You close the fire triangle, you start burning your material, and you're left with nothing. All your material is just burnt off. So that's why you need to maintain an inert atmosphere, using gases like either nitrogen, argon, or any other gases, inert gases available that you have. So we go down to a high temperature furnace, which is electrically heated. And so, as I mentioned, there are some simple unit operations like milling, where you could use the coffee grinder, but there are some complex processes where you have to use specialized equipment. So this is not done in any random furnace or any random oven. We use a specialized high temperature furnace, that is explosion proof, that is capable of inerting and all those things, and getting to really high temperatures greater than 1000 C. So this process of going from a very heterogeneous material which has all these random functional groups to a very ordered material which has these nice planes of graphite that you start forming is called as pyrolysis, which is very prevalent in the industry these days, and a lot of people use this to make high temperature heat treated materials or nanomaterials. So you can see when I was talking about the very disordered, very heterogeneous and randomly placed material with multiple functional groups, you can imagine it being like these small domains which are not getting together. And so you don't have an ordered material. But as you start heat treating it, taking the temperature higher and higher, when you get to 800 C, it starts forming itself a little bit, because it starts losing all those functional groups that were making it, giving it hindrance to make this nice plane of sheets of carbon. And as you keep on going on increasing the temperature, you make more and more carbon rich material, which is the end form is called as graphitic carbon, which is very similar to the graphite that we have, for example, that's used in our pencils, or any other general applications where graphite is needed. So this process gets you to greater than 90% carbon content. So now we've successfully gone from a sludge like material, dried it, understood what its structure is, what functional groups it has, to down to a nice fine particle material, which is carbon rich and which is very close to now in functionalization as carbon black, that we want to get to our product. So this is just a process flow diagram of the furnace that was used to make this carbon black material. And if you have more doubts, we can come back to this and discuss this process flow diagram if you want. The other very important technique that I was previously talking about is knowing how many functional groups are there in your material. So these two spectroscopy techniques are very important. So NMR is nuclear magnetic resonance, and FTIR is it's an infrared radiation technique that hits the radiations with certain wavelength on your material, and it detects how the molecules are vibrating in that material, and it knows what bonds are there in your material. And NMR does the same, which shows you how many functional groups you have on your material. So as you keep on increasing the temperature of your material that you're treating it with, you finally get to a material which shows a fingerprint that is very close to carbon black. So you don't have to be an expert in this technique to understand that when you have an overlaying fingerprint, you are very close to the material that you want to get to. And even in FTIR, you have a very little bump here, wherein carbon black is a flat line, which shows that you don't have any functional groups in carbon black present. So that's your goal. You're reaching there by doing that cycle continuously of finding processing, unit operations, characterization, see how it works, come back, repeat that process, understand the structure property relationships. Um, and then there's another step that we add, which is a milling step, because we reduced our particles to fine particles, but they were not fine enough. So we go to a technique that is more efficient, and that is planetary ball mill. I think we have a ball milling equipment in our department also in the SFMO lab. So you guys, I'm hoping you guys must have seen the ball mill. So what ball mill does is it has these media balls, metal balls, that when the mill is turning, because of the action of those media balls, when they hit the material breaks down because of the force and momentum and hardness of those media balls. So this equipment is very helpful in going down and breaking down the particle size. So now we are at a size where where we cannot physically use the sieves that I was talking about, to know how much particle size breakdown has happened. So there's another technique called as tin strength, wherein you add your material to a mixture of oil and make a paste out of it. And depending on how dark the paste is, you know how fine your particles are and how they are going to distribute in the natural rubber. So a lower and lower value means better and better, smaller and smaller particle size and darker paste. So it gives you a good evaluation of what you're doing with your ball milling parameters and are you getting there or not. So the target is roughly 35, and with higher and higher milling times, you reach to that target, and you eventually have this material, the hydrothermal carbon, which is carbonized or pyrolyzed, as I was showing you, and milled, which is a now a very satisfactory material to be added into the rubber, where you have good efficiency and good reinforcement, making the rubber stronger. So coming back and checking in with all the things that we needed to do, surface activity was surface activity was tuned by our inert pyrolysis, and by checking at different temperatures, we know that we can drive off these groups, functional groups, and make a nice material. And depending on how high your temperature is, you also start making these pores in your material and creating more favorable material that has higher surface area. Aggregate fineness by various milling techniques, as we saw those larger chunks broken down using a coffee grinder, and then later some of those non-visually representable large particles being broken down by milling, as we checked using the paste method. And then the OAN structure, which is a specialized method um, to check how long these chains of particles are. And we tuned that by multiple techniques because we saw characterization and we checked time and time again. It changed due to milling. It changed also when we changed the feedstock. So it is also dependent on the feedstock and time of pyrolysis treatment in the heat treatment unit. We have everything that we need in terms of physical and chemical properties now, but we faced a huge issue wherein our material was not getting added properly into the rubber, and getting mixed, because you can see how it struggles to flow out of the jar. So imagine having a conveyor belt, making it flow and dropping it down. It's going to rise up as a very light powder and create a dust, and you will lose more than 50% of your material, and it won't get added to the rubber that you intend and process properly. So very weak reinforcement, and you lose a lot of material. So compared to carbon black on the left, see how free flowing carbon black is, but not our material. It's struggling to come out of the jar and also dusty and spraying everywhere. So a very big physical handling issue of dusting and flowability, which also presents a lot of risk, safety risk, when you don't clean everything properly, and eventually it can deposit on a lot of equipment surfaces and have certain other implications. So how do you do that? You go see how carbon black particles are agglomerated. Um, so a unit called agglomerator or pelletizing unit is used, which uses these basic principles by swirling, rotation, and lifting of the carbon black, the fluffy particles, adding a binder to it. And the binder can also be mostly water, wherein the particles bind together because of presence of water, and then you dry off the water and make those nice free flowing particles. But this is $1 million equipment, and you don't even know if that will work for your material or not. So what do? You again start going looking around for inspiration in day-to-day things that you use. Apply these first principles, the techniques, the science that's used behind making this equipment, and see if you can find anything. And you can think of a food processor doing a similar job, wherein it can raise those fluffy particles, make them swirl and rotate, and with a minor modification of a spray bottle attached to top of it, you can spray your binder and your particles agglomerate. So we've gone from these fluffy, very light, dusty particles to now free flowing agglomerates, which are not the initial agglomerates that we saw. These can be easily broken down into, again, a fine particle like this when they go into the rubber, when they're added into the rubber for better processing. So now there's a comparison on the existing material to carbon black, and problem solved. You cannot identify which material was which. So it has all the chemical, physical, material handling properties, and addition that we want ideally for our material to be a carbon black like to like replacement made from biomass instead of making it from crude oil. So we go from wet, very wet material, sludge like, to a dry material which is not good enough for us in terms of the particle size. It has these huge chunks. Then we break it down, we carbonize it or pyrolyze it to make it high carbon content material, and then we mill it again to make it a fine powder. And then for handling and storage and transportation purposes, we just agglomerate those using water. It's not those functional groups that were binding them together, but it's only water, which is driven off in a very easy drying process, and then added to your rubber, which now gives you all the properties that you need. And now we formed a like for like product, which successfully replaces um, carbon black that's made from crude oil. And that's it. This is the flow chart that we now come up with, as I explained. So what's our summary, or what are our conclusions here? So if you're thinking of making innovative products, or finding a like for like product replacement for crude oil type materials that we are heavily dependent on these days, um, the key is to identify what's the structure that you're starting with, what property will your structure of your material impart in the final when it's acting as a final product. Understand those, form nice matrix of what happens when you change certain things and when you tune certain things. um, and also go back to all the literature, all the research that's been done on carbon black or whatever product you're trying to replace. They should have more than 50 to 100 years of research in that material, and understand what they do, what sorts of processing they use, and how does it change that material. So what impacts is it has in it being a final product, and take inspiration from that to tune your material structure to get good properties, ideal properties. And I'll always keep coming back to the first principles. When you're trying to prove something, you don't have to always make large equipment or go to a big company that'll do all the processing for you, and then find out that, oh, this doesn't work for me, and you wasted a lot of time and effort in it. So take inspiration from day-to-day things that you use. They're all based on these basic principles, basic scientific principles that you know, as a part of all your chemical engineering syllabus that you've learned. What do different unit operations do? What do different processes do? Things like that. And then building a robust process flow chart or process flow diagram of what do you need to do. And you've proven you got a product. Now start thinking towards scaling up and making a large commercial plant out of this, that you'll have a lot of customers for, which also has a very big advantage of being a sustainable product because it's made from waste biomass. So that's it. And you can ask me questions if you have on all these things.
Okay. Students, if you have any questions on this topic, you can ask either write in chat box or you can raise your hand so that I can unmute you to ask the question.
Yeah, you can also ask me any other questions related to higher studies in US. What is the scope of chemical engineering in US? Where do chemical engineers usually work? How difficult or how easy is it for chemical engineers to get jobs here in the US if you're an international student, and those sort of things.
Question is there, Anvit, in chat box. If you are able to see, you can see.
Oh, chat box. Okay, so the question is, the product produced from biomass is of same demand as that of conventional products in the market. So the answer is yes, the demand is same, because if you are able to build like for like replacement from biomass, it has an added benefit of being something that's a sustainable product because it's come from renewable resources. Um, and in the end, what matters for your customer or for a company who's using carbon black as a tire filler is the price and the properties. So you've taken care of the properties that your product imparts, which is same as carbon black. So it should have the same demand. And the other thing is price. If you price it at a very high price, nobody is going to buy it. People do care about sustainability and renewable resources and stuff, but any company, if they have to pay double the price, they'll always go back to the crude oil type product. So it is important to replicate all the properties, get a like for like replacement, then you'll definitely have the same demand.
One thing I need to add that your juniors should know, Anvit. So Anvit is a pass out of batch 2014 basically, and he was a past chairman of Science. And he has came up with one of the interesting events in the science that is robotics. And that event was lasted for 2 days with almost 200 plus crowd. That is a big achievement during the reference event that he had. Robotics. Right?
Yeah. Chemotics is, yeah, it was very interesting.
Another big event at that time.
Yeah. Yeah, we
Cellulose.
used, yeah, it was fun to combine robotics and chemical engineering and do fun stuff that everyone enjoyed. So it was very much, yeah, we burnt sodium metal in open air and water. So had to get permission from principal sir for that. So that was very interesting too. And nobody got hurt. So
Can I ask you questions? You can ask any questions as you told on higher studies or kind of placements you are seeing, or what are things to be done after a graduation. Any kind of stuff you can ask him. He is quite intelligent to answer all these questions. Yes, Bhagyashree, Akshara, Dipali. Actually, many of them are on YouTube. Some of them are there on YouTube. Akshara.
so nanotechnology in chemical engineering. So